So today we're going to study shortest path algorithms, the problem that is known as SSSP, single source shortest paths. The single source shortest paths. What does that mean? You have a graph G, you have some vertex S, and for any vertex V, we'll say that DSV is the shortest path distance, and the problem is given G and a source S, and that's why it's called a single source. Compute all DSV, which is all for all vertices V. You want the distance. So you fix a source and you want the distances to all destinations. That's called single source shortest paths. There's also something known as APSP, which is all pair shortest path, which is to get the distances between all pairs. And sometimes there's just a single distance problem. Given S and V, just get the distance between S and V. So we will look at the single source shortest path problem. In this context, it's best to think of directed weighted graphs.
Hey, Sesh, could you put up the fast version
yes.
also?
Yes, I will.
Thank you.
Sorry about that.
That's okay.
Could you also make me a co-host, please?
Yes, I will. All right. Okay. So I think it's all there now. Okay. So we have directed weighted graphs. So we'll think of edges UV having a direction and a weight WUV. And so WUV and WVU may be different. These could be different values because the graph is directed. Now, if G is unweighted, and what unweighted simply means is that the weights are either 0 or 1, right, which is sort of the usual case that you see, then BFS solves single source shortest path in essentially O of m plus n time. Right? If we run BFS, and because we initialize the predecessor array to all null, so that's the O of n, and then we can run BFS from S and we get a solution. And today what we're going to look at is how does one solve SSSP, single source shortest paths, in weighted graphs. And so we'll think of G represented as an adjacency list. Right? So the way to think of the list is, let's just say this is the list for U. So you can think of the object would have the vertex, the neighbor, and the weight. And then there is a pointer to maybe another vertex V prime, and you have the weight U to V prime, so on and so forth. So the representation of the adjacency list would actually contain the neighbor as well as the weight. And the length of a path, S U1, U2 going up to UK, the length of this path, and I'm just going to denote S as U0 so that the formula is nice, is going to be the weight of UI to UI plus 1, where I goes from 0 to k minus 1. That is the length of a path S, U1, U2, so on and so forth, which is not surprising. It's just the sum of all the weights. Okay? And so...
I know you have a raised hand.
Yeah, go ahead.
I think you just answered.
Okay.
Sorry. I think you just answered my question.
All right. Okay, so this is the weight of a path. And so DSV is the length of the shortest path, or you can think of as the minimum length of a path from S to V. So here is your graph, here is S and here is V, and you could imagine there being multiple paths that go from S to V, and so the DSV is the length of the shortest path that goes from S to V. Now, when we define shortest path in this manner, we have to be careful, because what if weights are negative? So, when weights are negative, DSV might be, ill-defined or not defined, or I'd say might not be defined. And specifically, when there is a negative weight cycle, then DSV may not be defined. So what is a cycle? A cycle is a path that returns to itself. That's a cycle. Now, to give you an example, here's a graph, and the graph is actually undirected. So here's S and here's V, and let's say the weights of these edges are all 1, and the weight of this edge is -3. Now the problem is there isn't a properly defined shortest path, because if you go from S and you go to this vertex, which is shaded here, every time you follow the cycle, the length goes down by 1, right? Because it's 1 minus 3 plus 1, right? Which is -1. So the weight or the length of that cycle, the total length of that cycle, is actually -1. So a shortest path would just keep taking that cycle over and over and over again to keep reducing its distance. And in some sense, the distance between S and V would, essentially be -infinity. It's actually ill-defined, or it's not defined. So when there is a negative weight cycle, the distances are actually not defined. Especially on the cycle, there is no distance, because you can keep taking the cycle and keep reducing the distance. Remember, nothing about this definition says you cannot take the same vertex again. You could have a path that just goes through the same vertex again. That's fine. In general, you don't expect that to help. But when the weights are negative, you can have negative weight cycles, and then it might not be defined. You can have situations where the weights are negative, but there is no negative weight cycle, in which case distances are defined. So for example, if this was 2 and 2, then you don't have a problem, because the distance from S to V would be, you go 1 plus 2 is 3, minus 3, which becomes 0, and then you take that to go to 1. So in this case, the distance between S and V becomes 1.
Professor, there's a couple questions
Yes.
About what is the purpose of weights, and then Nathaniel also has raised hand. You want to know?
In the event of all negative weights, is that perfectly fine as well?
No, if all the weights are negative, again, if there is a cycle, then the weights become negative. I mean, then the distances all will go to minus infinity. Or, I mean, that's a bad way of saying it. But the problem is you define DSV as the minimum length, and the minimum length is now undefined. Unless you were to look at the maximum length in that case, and then it becomes defined.
If there are no cycles, but all weights are negative?
If there are no cycles, then your graph is a forest, in which case there is exactly one path between any pair of vertices, or at most one path if they're connected. In which case, then everything is defined. Because if your graph is a forest, then everything is defined, because there is only, if two vertices are connected, there is a unique path between them.
I had a question about negative weights.
Yes.
What kind of applications would you use negative weights?
I will give you I will give you some questions actually in the question bank where you use negative weights. Sometimes it sometimes happens in what are called bartering systems, where I can think of these different nodes as goods, and if I want to sort of convert one good to another good, then how much profit I make, and then a negative weight would be a loss. So negative weights do come up over there.
I see.
As far as where do weights come up in general, well, you go to Google Maps and you type distances, and you type two locations and it gives you a path, and it's using weights, because essentially every road in the network, there the weight is actually kind of like the time it takes to go from one end to another end. Or it could be the distance. In the case of Google Maps, it's probably time, because it'll often take you to a slightly longer path if it's faster. I mean, it's much more complicated what's happening under the hood there. But there you can think of weights being distances, like actual how many miles is a road. You can think of the time it takes given the speed limit. That's another measure of weight. You can also think of, in a computer network, often if you're sending a message from one to another, there could be a measure of latency, like how long does the message take to get there, and that'll be a measure of weight, and then you try to find the shortest path. What is the fastest way of routing? So when you're accessing content online, there are basically under the hood somewhere there's some kind of shortest path. There's some routing that's being done, which is finding a path, and often you want to find the shortest path. Might not find the exact shortest path, but it finds a fairly short path. Any other questions? All right. So let's continue. So I'm going to define, before I actually define specific algorithms, I'm going to define sort of a higher level strategy that a lot of algorithms maintain. And we'll see that with that strategy, we can define different algorithms. And they all go through a key idea. And so if you think about it, this is in some sense also inspired by BFS, but BFS maintains a predecessor array. And we will also maintain a predecessor array here, and we'll also maintain distance. So whatever algorithm that we have, the SSSP algorithm, the single source shortest path algorithm, maintains two arrays. So we'll assume that the vertices are numbered 1 to n for convenience. So the first array is an array that's called dist. So the dist is going to be an estimate of the true shortest path distance. It's not going to be the true value. It's going to be an estimate that keeps improving as the algorithm keeps running. And the second is just a predecessor. And you know what the predecessor is. It's exactly the BFS predecessor. And it's a vertex preceding V on a shortest path from S. Now remember we discussed in the previous lecture, we discussed loop invariance and how we defined BFS, we discussed, we understood BFS, and then we discovered what the invariants are. Here I'm going to go the opposite direction. I'm actually going to tell you what the invariants are. There are certain invariants that these arrays are going to maintain. And then what we will discuss is we are only going to perform operations that maintain these invariants. So what are the invariants? So the first invariant, so this will hold at all times. This will hold at all times. The first invariant is that dist is always an upper bound on the true shortest path distance. So this will always be the case that dist v is an upper bound, meaning that it's greater than equal to the true shortest path distance. And the second property is v, the predecessor of v, the predecessor of the predecessor of v, so on and so forth, going back to S, is a path in reverse from S to V of length dist V. So what is this saying? This is saying that the way to think of this is that at any stage in the algorithm, so here's S. S is going to maintain some tree that it has seen so far. Okay, so it's got some tree. So what we get and what we are storing is for this tree, for any vertex, we have a path that goes from S to V, and we're storing the tree and the length of the path. And that's what's being stored. So another way to think of this invariant, or to think of the data structures being maintained, is really that S is maintaining some guess for the shortest path tree. So it's maintaining this guess for the shortest path tree, and it's going to keep updating this guess. And the tree is maintained basically by the predecessor array. It is also going to maintain the length of the path in that tree, and it's going to call that dist v. So it knows that the true shortest path is less than equal to, the true shortest path distance is less than equal to the distance, because the distance is a specific path. The algorithm will maintain this at all times and continually try to improve this, maintaining these invariants. So it's always going to maintain a guess for the tree. So it's always going to maintain a tree, and it's always going to maintain these properties, which, I mean, these are both equivalent. Like maintaining the tree is equivalent to maintaining properties 1 and 2. Any questions about that?
Yeah.
Go ahead.
Yeah, for part 1 of that invariant, when distance v is equal to the distance of S of v, is that effectively when you found that shortest path?
Exactly. So what you want to argue is that when you terminate, then actually the condition 1 should be an equality. Right? That's what the proof is going to do. Yeah.
I also have a question.
Yeah, go ahead.
So basically, this algorithm just like runs. They just like first find a random path and like try to optimize it.
No, I have not told you what the algorithm is yet. The algorithm is going to be sophisticated, or it's going to be, so I'm just telling you, giving you like the basic idea of the algorithm. So given that we've talked about BFS, and you hopefully, given the discussion on BFS, you understand this notion of predecessor maintaining a tree, because you have this view in your head, it's much easier to define these algorithms once you just take that view. Instead of, if I were to go ahead and write down the pseudocode of the algorithm, it will make less sense. When you think of it really from, it's maintaining a guess for the shortest path tree, it's going to maintain a tree, and it's going to find out some way of improving the tree. And when it can do an improvement, it goes ahead and makes the improvement and keeps doing improvements until it cannot improve anymore. at which case we can prove that all the shortest path distances have been discovered. Questions? All right, so far so good. So these are the invariants of the algorithm. And again, the way to think about the invariant is that it's maintaining some guess for the shortest path tree. Now let's talk about the initialization. And the initialization should not surprise you. So the initialization is simply to set dist of s to 0, and for all s not equal to v, the dist of v is equal to infinity. I should say for all v not equal to s. For all v not equal to s, the distance of v is infinity. And then for all vertices v, the predecessor of v is null. And this is how we initialize these data structures, or rather these arrays. Now that we have the invariant, we have the arrays, the invariants, and the initialization down, I'm going to give you the key subroutine to essentially all shortest path algorithms. The subroutine is basically, it's called a procedure called relax, and it's called relax because this is related to relaxations of certain linear inequalities. So relax is going to take two vertices, and it's going to have width, technically it's a pointer to the edge uv. So instead of thinking of it two vertices, you can think of it as actually it's a pointer to the edge uv. And if uv didn't exist, then relax is not going to be called. It's only going to be called on edges. Okay, so it's a pointer to that edge. And so it's a very simple operation. It says if the distance to v is strictly greater than the distance to u plus the weight to uv. So what is this saying? It's saying suppose you're at s. And so here is u, and here is v. So we already have an estimate to the distance over here. And we have an estimate to the distance from s to v. If it's shorter to go to u and then to v, then you should make that switch. So if the distance to v, that is the current estimate, right? Distance is an estimate. It's not the true shortest path distance. If the current estimate is more than the estimate to u plus wuv, then you update. You set the predecessor of v to be u, and you set the distance of v to be equal to the distance of u plus wuv. So this is the procedure relax. So another way to think of this is, let's say you have S here and your predecessor has maintained some tree. And so you have some vertex V over here. And what you recognize is that instead of going along this path, it's actually better to go from V, it's actually better to go from S to U and then take this edge. Then what you do is you say, let's get rid of that part of the tree and let's put this edge into the tree. And everything else stays the same. So what it does is it basically replaces one edge of the shortest path tree that is maintained. That's what the predecessor is changing. It's changing the predecessor. The important thing, property, is that relax is safe, meaning that all invariants are maintained. And this is really important. The invariants are always maintained if you call relax. So relax is safe. So you can call it for any edge. Because if the distance v was less than equal to the distance u plus the weight of u to v, like if it turned out that the distance from s to v along this path is just shorter than this other path, then it doesn't do anything. It says, I'm not going to do anything. So you can always afford to call relax on any edge and the invariants are maintained. Questions?
There's a raised hand.
Yeah, so you can just keep doing relax recursively for every for all of them until you get the predecessor from S to V, right? You can just get the answer like that.
I mean,
the shortest path.
There's no recursion here, right? Relax is just an operation.
Yeah, no, but if you keep calling it recursively for every weight from S to V.
From every
I mean, the thing is, you have a path from S to V, and you explore the other path from S to U, and then if it is smaller than the dist V, you can keep doing that recursively for every vertex here, and then that way you can get the predecessor, which is the answer of the shortest path.
No, so it's not clear, because what if there exists a shorter path that goes like that? And you have not and the algorithm has not discovered it. I mean, the problem is if you keep calling relax on the same edge, at some point it's not going to do anything. Right? I mean, this only makes an improvement if it sees an improvement. What if you keep calling relax on edges where there's no improvement? Should you call it on another edge and then call it on this edge? So understanding the sequence of relaxations is the whole business of shortest path algorithms. That's like another way to think of it. So, I mean, essentially, our shortest path algorithm is going to call a sequence of relax operations.
Yeah.
And the question is, what is the most efficient sequence that can be called, which will guarantee that at the end you have shortest paths?
No, I was just thinking a brute force way.
So yeah, you could do it in a brute force way, in which case you would end up with exponential time, because there are exponentially many paths.
Yeah, exactly.
Yeah. Questions?
No other questions in chat or raised hands.
Okay. So let us now discuss our first algorithm, Bellman-Ford, which is a deceptively simple piece of code. So the first is just initialize predecessor and dist arrays. The second step just is for I going from 0 to n minus 1, and you can even improve it from 0 to n minus 2, it doesn't matter. For every edge uv, so this is a traversal. For every edge uv, just call relax uv, and that's it. That's the entire algorithm. So all it does is it repeats the following process n minus 1 times. It goes through every edge, calls relax once on all edges, then it goes back and does this again, and it just does that n times. And that's the algorithm. Let's understand what the running time of the algorithm is. So first, what is the running time of relax? What is the running time of relax? How long does it take?
Order 1.
It's order 1, exactly. Because you have a pointer to the edge. So all you have to do is look up the weight, and then you just have to make these comparisons. Now the initialization over here, this can be done in theta of n. The relax is O of 1, or theta of 1. This step over here takes theta of m, and this takes theta of m times n. So Bellman-Ford runs in theta of mn running time. question now is, why does it work? So the way to think about Bellman-Ford, I'm going to draw a picture here, is think of this as all the relax operations done when I is equal to 0. And then you've got a bunch of relax operations done when I is equal to 1. So on and so forth. So on and so forth. I is equal to n minus 1. And actually n minus 2 is enough, but that's fine. So think of these as, this is like, I'm just drawing a pictorial view of all the relaxation operations done here. So this is all edges, and all edges, and all edges. Okay, and we're going to come back to this picture to understand how Bellman-Ford works. Some properties of Bellman-Ford which are crucial. So one of the nice things about Bellman-Ford is that it works even when weights are negative. It can find a negative weight cycle. I'm not going to prove this for you. I'm going to leave this as an exercise. When I show you how Bellman-Ford works, I want you to understand that then you can go back and you can answer this question. So I'm going to leave this question as an exercise for you to do once I discuss how Bellman-Ford works. Go over and look at it, understand it, and then you will see why it can find a negative weight cycle. Okay, so what is the logic behind Bellman-Ford? And again, it's deceptively simple. It's an incredibly beautiful argument. So what Bellman-Ford says is, okay, so let's just look at the true shortest path from S to V. So here's some shortest path. Okay, so I'll call this U1, U2, U3, up to UK minus 1. I'll just call this as UK, call this as U0, just for convenience. So this is the true shortest path. Now suppose, and this is sort of related to what was suggested in the comment a while back, suppose we called relax SU1, relax U1, U2, relax U2, U3, so on and so forth, until we got to relax UK minus 1V. Suppose we called these relax operations in this order. In this order. Then dis to V will be exactly the shortest path distance. Right? So if you could magically call relax in this order, so first on SU1, then on U1, U2, then on U2, U3, exactly in that order, then you're guaranteed to find the shortest path distance to V. Now, how many edges are there? So the number of edges in any shortest path is actually at most n minus 1. We're at most n minus 1 edges. At most n minus 1 edges. So if we could call relax S of U1, then U1, U2 in this order, the distance will be, okay. Now remember that relax was a safe operation, which means, suppose we called it in the following order. So we do relax S of U1, and then we call a bunch of other relax calls. So we do another bunch of relax calls, and then we call relax S of U1, U2, and then we do another bunch of relax calls, other relaxes. Then we do relax U2, U3, and then you do another bunch of calls. I don't know what these calls are. They could be anything. It doesn't matter. And then we call relax U3, U4. So on and so forth, and we do a bunch of other relax calls, and then we call relax UK minus 1 V. Suppose this is what we did. So first argument was, suppose you called it in this order exactly, one after the other. Then the distance of V is going to be d of SV. Suppose we actually interspersed these relaxation calls along the path with other relax calls. It's not going to make a difference because relax is a safe it's a safe method. The invariants are not going to change. The invariants are not going to change. So we're guaranteed that by the time we do all of these calls, dist of V is going to be dsV. Okay, does this argument make sense? Any questions about this argument? Because this is the key. Right, this is saying if you call relax, you do another bunch of relax calls, then you call relax of U1, U2, do some more relax calls, then call relax U2, U3, so on and so forth. You are guaranteed by the end of this process to get dist V to be the shortest path distance from S to V.
Is this also proved by induction?
You can formally prove it by induction. If you wanted to write a formal proof, you do it by induction. You would do it by induction on the number of edges in the path.
Okay. So in my head, this is what I have, right? If you have a opposite facing C, and then you join both the corners, and that C is U1, U2, U3 till K minus 1, and the opposite sides are S and V. It just doesn't make sense that if the distance of dist V is equal to the shortest S and V.
This is a shortest path. So I'm assuming, suppose you knew what the shortest path was. I'm not giving an algorithm here. I'm giving an argument, a proof that Bellman-Ford is correct. So I'm doing a thought experiment. And my thought experiment says, suppose you knew what the shortest path is and you could call relax to all of those edges in that order, then you're guaranteed to find the shortest path distance.
Okay, I guess it makes sense, yeah.
Now, you could say, how do you know what the order is? And you're right, we don't know what the order is. But suppose you could do it. And suppose you did it even with other relax calls in the middle. It's still going to give you the shortest path distance. Right? It's still going to give you the shortest path distance. So now let's go back to our figure here. And we know that in this first block of calls, there's going to be some call of relax S of U1 somewhere in this list. Somewhere down here, there's going to be a call of relax U1, U2. Somewhere there's going to be a call for relax U2, U3 in the third block, so on and so forth. And so we're guaranteed, there's going to be a call to relax, let's just say that it was, drop this. I'll say let's look at the I equals 2 block. Somewhere over here there's going to be a call to relax U2, U3. And so because we do this n minus 1 times, we are guaranteed to call those relax operations in that order. We're going to do many more calls than we need, but that's okay. We are guaranteed to call the relax operations that I stated over there in that order for every shortest path from S. Right? Because when we initialize, we start from the correct shortest path to S. And so after the first block of calls, we'll have the correct shortest path to U1. After the second block, we'll have the correct shortest path to U2. And then we'll have the correct shortest path to U3, so on and so forth. And so by the time we end up at V, we'll have the correct shortest path. You will not have the correct shortest path to V after this call, after this block of calls. but you will have it after k blocks, where there are k edges in the path. And there are at most n minus 1 edges, so this is enough. So technically, again, you only need n minus 1 blocks, so even up to going up to n minus 2 is enough. So that's the logic behind Bellman-Ford. Once you understand this logic, you'll be able to see how it can find negative weight cycles as well. But first, does this logic make sense? Questions?
I had a question on your for loop for every edge.
Mm-hmm.
Is that just every edge from the vertex that you're on?
No, every edge in the graph.
Okay.
Right? Every edge in the entire graph. So you're traversing the whole graph.
How are you finding U1, U2, U3 in order?
You're not. That's the surprising part. You're not finding it. You just know that it's going to come in order. Because you're making a call for all the edges. And then you're making a call for all the edges again. And then you make the call for all the edges again. So somewhere you're definitely going to call relax SU1 before you call relax U1, U2. You will also call relax U1, U2 in here, but that might be in the wrong order. But that's okay. You're allowed to make more relaxed calls. It doesn't affect anything.
Just to clarify, it pretty much fixes itself as it runs.
Exactly.
Okay, so tell me if I'm wrong. So you're making all the calls in the first block itself till V, but
not to V. No.
Not till V.
You're making it for all edges in the graph.
All edges in the graph.
So these blocks have the identical set of calls, right? Because if you look at the for loop, there's nothing changing as I changes.
Only the order changes.
No, the order also doesn't change. Nothing changes. You're just repeating the same set of calls n times, or n minus 1 times. You're simply repeating these relaxed. It's like, okay, so you have this line of code here, right? You're simply running this line of code n minus 1 times, or n times, and that's it. So in this block, when you fix I, you have a block of relax operations. They're all done in some order, and you don't know what the order is. But if you do it again, then you're guaranteed that for any pair, you're going to call this one first, and then this one second. You may call other things in the middle. You may actually call relax U1, U2 again over here, and you will call relax S of U1 again in the second block. But all you need is that somewhere down the line, if you can make a call to relax SU1 before you made a call to relax U1, U2, that's good enough.
This sounds like magic.
Yeah, that's why it's very surprising. It's a deceptively simple piece of code with a deceptively short argument of proof. But you really have to go and think about it.
So basically, it's just like when you iterate into the ith loop, the first ith element for every index will have like the all permutations, like what we call.
Exactly. That's another way of thinking about it. When you put all of these blocks together, then you essentially get, if you take any set of edges and you permute them in any way, you will have called all of those relax calls in that order for any permutation of any subset of edges. So what you stated is a slightly more general version, but that's the key idea. You're able to basically, it's almost like brute force in some sense. It's going over all possible permutations, but what's clever is that it only uses m times n running time. It doesn't do n factorial or m factorial. It doesn't go over all possible permutations, but it implicitly is able to cover all possible permutations. It's very clever, very clever.
Professor, what is n in the line 2?
I'm sorry, what is which? N?
N, yeah.
Yeah, n is the number of vertices.
Okay, thank you.
It's the number of vertices. M is the number of edges.
Ryan, you have your hand raised?
Oh, yeah, thanks. So just to clarify, we go over it to the main loop, or sorry, the outer loop n times, because the shortest path could theoretically go over every node, and so we have to do it like n times.
Exactly. So if you think about it, if you ran this loop only k times, you will discover all shortest paths where the shortest path involved k edges.
Yeah, because the stuff that's used kind of past k edges, the distance to there hasn't really been calculated yet because it's still kind of infinite.
It might not be infinite because you're doing all kinds of relaxed operations. So maybe it's finding something. You don't know. It's a little hard to determine what's going on because there could be a very short path to a vertex. I'm sorry, there could be a path which has like 2 edges to a vertex, but each of those edges, they might have huge weight.
Okay.
Right? So it won't be infinite, right? So you could have a situation where you have something like this. S and V. And let's say this edge has weight 100 and this edge has weight 100. And there are 5 edges each of weight 1. So what happens is after 2 iterations of that block in 2, the distance to V will be 200. Dist will be 200. It's going to take 5 iterations to basically get that distance down to down to 5. If that makes sense,
okay.
Right?
Yeah, that definitely makes sense. Thanks. Yeah. That clears it up.
Yeah.
But it's also possible can be like this dump can be 5 in like 1 to 5 iterations, like in some place. Not have to be 5.
Say that again.
So like you said, after 5 iterations, they will reduce to 5 instead of 200. But like it's like definitely less or equal to 5 iterations. Like they can be happening in any times in
it could be it could be shorter, but then that would be so then. But assuming that this was the entire graph. But you're absolutely right. There could be other edges that would bring it even faster. But my point is, because there are weights, there is a distinction between the number of edges on the path and the length of the path. Just because a path has few edges doesn't mean that it's short with respect to the weight.
Yeah, but like in the iteration 0, like first iteration, you can like magically call this path in this order, so they will directly show to 5 instead of 200, right?
I see. Yeah, no, good point. You're right. You're absolutely right. Yes, you're absolutely right. So if it so turns out that in the first block, all of these 5 calls are made in that order, then you would have the distance being 5. That's right.
Yeah.
So you're right that it could, so I stand corrected. So you're right that in less than 5 blocks, you may actually call all of these in exactly the right order and then you'd be done. Right.
I guess I want to ask why is it different? Why is I equals to 0 and I equals to 1 not the same order? Because we're not really changing anything.
They are the same order. They are precisely the same order. But you're now looking at the order where you pick something from the first block and something from the second block. You're not looking at the order within each block of calls. You're looking at the order across various blocks.
Oh.
That's the key. You have to look at the order across the blocks, not within the block. Because within the block, you don't change anything.
I guess then it makes sense why U1 would be before U2 in the second block. Because of the order.
It could. Okay, so what could happen here is that the relax U1, U2 call could be before the relax SU1 within the first block. But this call is repeated.
But then, I get it. Now I understand. Yeah. It's even if it's repeated, it's still in the order.
Yeah.
So I have a question where, why would you ever use this over something like BFS?
BFS cannot handle weights.
Oh, I see.
BFS can only deal with the case when the weights are 0 or 1.
Oh.
This works even when the weights are negative. It still works. As long as there's no negative weight cycle. If there are negative weights and shortest paths are defined, then Bellman-Ford works.
Okay.
It's an amazingly simple algorithm. right? I mean, you could code this up in a jiffy, right? All you have to do is you have to code up the relax operation. I mean, once you have your graph data structure, you code up relax, and then you just code this up, and that's it. You have a shortest path algorithm. Okay, so that's Bellman-Ford. Again, as I recommend with all graph algorithms, the best way to understand it is to take a small example, 6, 7, 8 vertices, draw a graph with a bunch of weights, run this step by step, and it will take an hour, it will take maybe an hour and a half. Do it with a few friends, over Zoom or something. But run it together. Run it step by step and see what's going on, and then you'll see how it works. It'll make a lot more sense. This is a very clever piece of code, and the problem with clever pieces of code is they take a long time to understand. Right? So you have to really go back and think about this. Now that we've talked about Bellman-Ford, we can talk about Dijkstra's algorithm. Now, what is the benefit of Dijkstra over Bellman-Ford? So let's actually first look at what is the downside. So it's not a downside. Dijkstra assumes all weights are non-negative. And this is crucial to Dijkstra working. So what Dijkstra says, and the idea of the algorithm is, if you think about going back to Bellman-Ford, it seems like it's extremely wasteful. It's making all of these relax calls when maybe not all of them are needed, because it's going ahead and copying all of these calls again. Many of these relax operations probably won't even do anything. It's likely that many of these calls are not going to make any effect on the graph. So what Dijkstra says is, when it makes a relax operation, it wants to make it count. Bellman-Ford says, I don't care, I just do it all. And the benefit of that is simplicity of the algorithm, but the downside is that the running time is quite large. M times n is quite large. And so if you think about Google Maps cannot afford to do Bellman-Ford. Especially if you're looking at distances that are sufficiently far apart, Bellman-Ford is a bad idea. So what Dijkstra says is the best way to understand Dijkstra is to have this sort of picture in mind. So let's just say that S, I'll call this set capital S, and say all shortest path distances in capital S have been found. So let's say that you're at a stage where there's some set of vertices where all the shortest path distances to those vertices have been found. Initially, capital S is just the singleton vertex little s. So what it says is, if you look at an edge that's out here, there's no point of calling relax on that. No point in calling a relax operation on the edge that is so far away. Instead, look at these edges that are going out. Right? And so I'm just going to draw a little boundary here. I'm going to call this the frontier. These are the vertices where shortest path distances have not been found, but their neighbors have shortest path distances that have been discovered. Okay, so remember that maybe this thing could have multiple edges in here. And so let me zoom in on the frontier at some point. Okay? So I'm zooming in onto the front. This is the discovered set. So here's S somewhere here. There's U and U prime. And so shortest paths from U and U prime have been discovered. Now let's look at some vertex outside. Let's look at V over here. Now the claim is any shortest path to V, has to go from within S and then somehow get to V. Any shortest path has to go from within S and get to V. Which means if something like this happens, then let's look at the first edge that leaves the frontier on this path. So let me call this V prime. It means that V prime has a neighbor who's in this set. So we should, instead of finding the shortest path to V, we should find the shortest path to V prime first. It's kind of like saying that you should grow the frontier step by step, or you should grow S step by step. So the idea is, and I'll make this more precise, you find the least weight edge leaving S. And the least weight edge is the one to relax. It's not entirely that. It's something close to that. So it says when you discover all the shortest paths within here, you know that any shortest path going to any vertex has to go from within the frontier and go out. So you find like the first edge that should go out, and you call relax on that edge. And if you do this, you can save on trying to sort of call it blindly the way Bellman-Ford does. So you choose the order of the relax operations carefully. Okay? So another way to describe this, so I'm going to say this again, is let's do the following instead. Let's do a version of Bellman-Ford. Let's do a version of Bellman-Ford where instead of doing it over all the edges, we only look at the edges in the front. We're only going to look at edges in the frontier. So we'll say for every U in S, okay, this is not the algorithm. I'm just doing a thought experiment. For every edge UV. So remember, unlike Bellman-Ford, which just does it for all edges, I'm only going to do it for the U's that are in the frontier. For all the edges UV, I could call relax UV. So this is going to work. And this is going to save you on some calls. Instead of doing it on everything so far, you only look at the edges in the frontier and you only make calls on that. Now Dijkstra goes even one step further from this and says if you're more careful, you don't know if all of those edges are really going to be helpful. Because it could be that, for example, this vertex has got multiple edges that are going in here. Sorry, V has multiple edges going in here. But the shortest path to V is actually going through V prime. So you don't want to actually call relax on these edges. Another way to put it is you never want to call relax edges. You never want to call relax on edges that are not going to be in the shortest path. But this is like a chicken and egg problem. You're calling all the relax operations to find the shortest path. And so what Dijkstra does is in some sense kind of get some meat in the middle over here. It actually is able to call relax operations only on the edges that matter. Okay, and the way it does that is, now let me just say instead of calling relax, let me just do something else. Let me just consider what happens when you call relax UV. You end up by looking at distance of U plus WUV, right? That's what relax is going to look at. And so what Dijkstra says is find the minimum value of dist U plus WUV and call relax on that edge. This isn't an efficient implementation. I'll tell you how the efficient implementation works. But what it says is if you look at U in S, so S is the part where shortest paths have been discovered. You look at every edge that's leaving, that is leaving this set. That's the frontier. Now for each of those, this edge gives you a potential path to this vertex, because you could look at the shortest path distance from here, and then you look at the weight of that. And this gives you a potential path. You look at all the potential paths you can get, you look at the minimum one, and you only call relax on that edge corresponding to the minimum. Now again, this doesn't seem like it's really efficient because you have to go over all the edges. And so with a clever use of a min heap or a priority queue, we can actually make this efficient. Okay, so I've been giving sort of a high level description, but are there any questions about the logic? And I'm giving you this logic so that you kind of you're primed to understand what Dijkstra is doing. Again, the best way to understand it is to take a small example, is to run Dijkstra as I describe it, and then it will make a lot more sense. But this is the idea. So any questions?
Theoretically, we also have to recalculate the shortest paths inside of S once we do the frontier, right? Because considering kind of the picture you drew in the bottom left right now, the shortest path to U could be through a V prime.
No, so, right? Sorry, so I have defined S to be the place where all shortest path distances have been found.
Okay.
In this picture, yeah.
If, how could that be, how could we know for sure they're the shortest path if we haven't considered all of the, because it's all positive.
Yeah, right. Exactly. No, good. So it's because the weights are non-negative. If the weights are negative, then it fails. But because the weights are positive or non-negative, and you call them in a specific order, you can actually prove that you can find sort of a set where you actually have discovered everything. So here's one way of looking at it. Look at S. You obviously have the shortest path to S. Okay, so let's start with S. Obviously you have the shortest path to S when you begin. Look at all the neighbors. Now look at the edge of minimum weight. And let's say that edge was, so this is at, like say 5, 7, 20, 3, and 8. These are the weights. You know that the shortest path to U has to be 3, because any other shortest path is to go from somewhere else, and because all the weights are non-negative, every other path will have to have weight at least 3. Actually, it has to have weight at least 5. So you're guaranteed that this is part of the shortest path. And then you can kind of apply this logic again and again.
I have a question about that example.
Mm-hmm.
Couldn't you have done like a path from that U to like U prime? Let's say it was like a weight of like 20, and there was a path from the weight of 5 edge going from S that was like only weight of 2 that was also going to that U prime.
This has a weight 2.
Yeah.
Yeah, but then that's 5 plus 2 plus 20. So I'm just saying that you're guaranteed that the weight to U, you have the shortest path. You're right that the path to U prime is not going to go via U.
So you're still testing every path between S and U? Between
all of this set, exactly. I'm not going to just look at that vertex. I'm going to look at the entire set of vertices that I figured out.
Right, okay.
So now what I'm going to do is in the next step, I'm going to look at the edges that go out of S and that go out of U. Now let's just say that there is an edge here of weight 1. So this is 3 and this is 1. Again, I know that this is going to be your shortest path because any other way of getting out has to have weight at least 5. So I'm going to then extend this frontier, extend my S. And then at some point I extend it this way. And then eventually I keep extending. So it's going to sort of slowly extend its way. And every time it makes this relax operation, it always makes sure that it's going to extend whatever its knowledge. So it sort of extends this region where shortest paths have been discovered. And it does it step by step.
I have 2 questions. One is, you keep increasing the frontier, right?
You keep increasing actually S, not the, but you're increasing the region where shortest path distances are known, and you always look at the boundary to see where to extend it next.
Okay. And wouldn't it be easier to go from V to S rather than going from S to V?
So in this case, it's a directed graph, right? So it's really distances are calculated from S to V. So just want to make sure that is clear. But assuming that, no, it's actually better to go from S because you know that you have the shortest path to S. Just trivially. That's how you initialize. And so if you look at this picture, you'll see that instead of trying to look at some vertex far away and figuring out how it's going to get to S, it's better to look around S, look at all the information you know and kind of grow that carefully, and eventually you'll get to every place.
Yeah, but then there'll only be a couple of edges that, or a couple of paths that go from V to S, rather than so many paths that could lead from S to V.
They're identical, like paths from S to V. I mean, you're always looking at paths from S to V, right? It's directed. Yeah. The distance is from S to V.
And if it's undirected?
I mean, if it's undirected, then assuming that you just take every edge and you put 2 directions on it. But the argument is still the same. When you look at this picture, if you look at a vertex far away, that's U, you have no information about where the shortest path is going to come from. It's better to look at the region where you already know the shortest paths so that you can pick the next edge carefully.
Okay.
There are some raised hands. If Ryan, you want to go ahead?
My bad, he already answered my question.
They look like they left, so never mind. Anyways.
Any other questions? So I'm going to write the code for Dijkstra, the pseudocode, and then I'll take further questions on that. So again, this is not entirely obvious. You will need to go and run this on a small example. So let me now describe Dijkstra's algorithm, starting from the graph and S. So first step is we initialize dist and predecessor arrays. And well, okay, this is useful. S is an empty list. So S is exactly the set that I described earlier. This is the set where all things are found. And then the crucial data structure is Q is a priority queue. So think of a min heap. A min heap storing vertices with the distance as the key. So it's storing the vertices with the estimate of the distance as the key. Now this is where the main work happens. While Q is non-empty, so step A is, first it does an extract min from the queue. It's going to do an extract min on the queue. It's going to append U to S. So whenever it actually takes something from the Q, it says, I've actually discovered the shortest path to that. And then for every vertex in the neighborhood of U, so the picture that I want to draw here is, so here's some U, this is some S. What it's going to say is that once U has been extracted, S is going to extend out to that. Then it looks at all the neighbors. Looks at all the neighbors. For every neighbor, call relax UV. So it's calling relax for all of these. But once it calls relax, it also has to update the position in the queue. And decrease key in queue. Because when you call relax, the distance is decreased, so one has to decrease the key of V. Right? One has to decrease the key. And so this is sort of this is a heap operation. And so this is the procedure.
What do you mean by decrease key of V?
I'm sorry?
What do you mean by decreasing key of V?
Okay, so if you look at the queue, so the queue stores a min heap where every vertex has a key. The key gets updated. So you can also call it an update key.
Okay, got it.
Right? So it's decrease key or an update key. So what is the key updated to? So it's in the queue, it's updating the key of V to dist of V. Why does it have to do that? Because dist of V may have changed. Dist of V changed because of the relax operation. Because of the relax operation. Questions?
I have a kind of two-part question. One is, does this tell us anything about the structure of the graph, the way the breadth first search was sort of able to, or is that other algorithm entirely?
Well, I mean, you get a shortest path tree. So insofar as breadth first search gives you a shortest path tree, this is also giving you a shortest path tree.
But like in terms of connected components or
connected,
crosses or anything like that?
Not really. So you wouldn't use this for, that it doesn't tell you anything structural with respect to connected components, no.
And I guess one last is, would this detect cycles or just avoid them entirely?
So if this has negative weights, then it breaks down.
Positive edge cycles.
Positive edge cycles, this might not discover them. I mean, breadth first search is far more effective in discovering cycles. Like if you want positive weight cycles, I mean, you just want some cycle in the graph, then you would use breadth first search. This doesn't really get you information on cycles. Because if it really makes a lot of progress initially, it will start ignoring lots of edges. Whereas to find cycles, you kind of want to have to traverse all the edges.
Right.
I mean, you will find some cycles. Because eventually, this does touch edges and it gives you a shortest path tree. So you will find some cycles through this. But this is probably not the most efficient way of finding cycles.
I don't know if it's just me, but could you explain what cycles are you referring to?
So cycle just means that in any graph, like a path that sort of goes back to itself, that's a cycle.
Oh, okay.
And so when you have cycles of negative weight, as I discussed at the beginning of the lecture, then shortest path actually cannot be defined.
Yeah.
And Bellman-Ford can find negative weight cycles. Dijkstra cannot find negative weight cycles. Dijkstra breaks down when you have negative weights, even when there are no cycles. So Dijkstra is only used when all the weights are positive, are non-negative. Okay, let me discuss the running time. So the initialization, that happens in theta of n. All of, first 3 steps are all theta of n. Now let's look at the extract min. So this is a min heap. Every time you call this is O of log n, and this is called n times. Because once you remove a vertex, you never insert it back in. So this is called at most n times for all the vertices. Now this is a traversal of the adjacency list. And if you go back and you think about it, this block over here is called m times. It's called once for every edge, just like BFS. This is very similar to BFS because you have a queue, you get what's at the top of the queue, you look at all the neighbors, and you perform some operation. So every edge is touched once, or at most once, assuming that it's in the connected component. So every edge is touched at most once, so there are at most m times that relax and decrease key are called. So it's called m times, and so the total running time of this block over, so this block runs in O of log n, and this is called at most m times. So the total running time, is really, in the worst case you can also argue it's theta of m plus m log n. And so what Dijkstra gives you is m plus n log n. Using a fancier heap, and this is called a Fibonacci heap, you can actually get it down to O of m plus n log n. So you can improve by a log factor. But this is the main running time of Dijkstra. So there's a fair bit of ground that I covered. So what I'm going to write down, the next is like a summary page. And I want you to sort of keep that summary page just so that you know whether you've covered all the points for understanding shortest paths. So this is a summary of single source shortest paths. If G is unweighted, then you do BFS. And as we all know and love, it's theta of m plus n. Now let's consider the case where G is weighted. If there are negative weight cycles, then shortest paths are not defined. So we defined the relax operation. And sort of the distance invariance. So by the way, for the final test, which is test 5, which will be held at the time of the final, I will ask questions about shortest paths. So relax is a safe operation. It always preserves invariance. invariance. Okay, so an SSSP algorithm, a single source shortest path algorithm, the path is superfluous. A single source shortest path algorithm can be thought of as a sequence of relax operations. And so now we have Bellman-Ford, which can handle negative weights, meaning that when shortest paths are defined, even though there are negative weights, Bellman-Ford will find the shortest paths. Bellman-Ford can discover negative weight cycles. I did not explain that. I left that as an exercise. Please go and understand the logic behind that. You can draw a negative weight cycle in a small graph, run Bellman-Ford, and you'll see what happens. The running time is theta m times n. So remember, PFS is m plus n, this is m times n. So Bellman-Ford is definitely much more expensive in its running time. There is Dijkstra's algorithm. It assumes non-negative weights. It runs essentially in theta of m plus n log n. And it's a classic use of a heap, of a min heap. Min heap or a priority queue. It's a classic use of priority queues. So this page of text that I have here, this page of text, let me zoom out a little bit more. Is sort of my entire summary of today's lecture and of all the things that I've covered, which is a fair bit of ground. Again, as I said, when G is unweighted, then BFS finds shortest paths. This is something that we covered, so it runs in theta of m plus n. When the graph is weighted, when there are weights, then BFS does not work. If there are negative weight cycles, then shortest paths are not defined. We discussed the relax operation and distance invariance. We said that relax was a safe operation in that it preserves the invariance. The nice thing is we can think of a single source shortest path algorithm as just as a sequence of relax operations. Bellman-Ford can handle negative weights. Bellman-Ford is an incredibly simple, cute, very clever algorithm. It can discover negative weight cycles, runs in theta of m times n. Dijkstra assumes that all the weights are non-negative. It crucially uses that in its proof of correctness. And it runs essentially in what's called near linear time. It's m plus n times log n, and it's a classic use of a min heap or a priority queue. So what I'll do is I'll end the lecture here. Even though we have 5 minutes left, I'll take questions in the last 5 minutes because there's a fair bit of ground. I don't want to cover anything new, and so I'll take any questions that you have.